Good afternoon, everyone. Welcome to our pre-lab lecture. Our experiment today is on determination of percent content in acetic acid and standardization of sodium hydroxide solution. Just like last week, there will be a quiz at the end of the session. Please make sure that you have your calculator, you have the periodic table, and a couple of scratch papers so that you use in the calculation part. This lab also calls for reading and understanding the background procedure in TopHat in order to successfully complete the data sheet. I will walk you through the data sheet just like last week, how you will complete each and every item on the data sheet. To this point, there are some prerequisite concept you need to apply in this experiment as well. You may not really see it in the handout, but you are expected to know. These are, let me just share my screen here and show you those prerequisite skills which you should have. One, all right. One is the concept of molarity. All right, molarity. We say that it is what? It is determined by getting the number of moles of volume in liters of solution. We looked at it last time. That is equation you need to be able to use. All right. We will also use today subscript L for molarity in moles, and of course, number of moles. All right. Number of moles can be, if you are given the solid substance, it will be determined by taking the mass. All right, mass in grams of molar mass of a compound, molar mass. These are prerequisite equation you need to remember. We'll be using this equation. I know we can also find the number of moles here using the molarity. Molarity, all right? Molarity times volume in liters equals, this is equation 3, all right? Equation 3. I'm rearranging this equation 1 to get equation 3. Equation 2, you need to know that if you are given the solid compound, given the chemical formula, all right, or you use the periodic table to find the molar mass, you have yourself the number of moles. There is another equation which you learned a while back, okay? This is the density. Remember, density equals to what? All right, equals to mass in grams of volume. It can be volume in ml. It doesn't have to be in liters. Doesn't have to be in liters. We can rearrange this to get the mass. Okay, mass from the density equation is obtained by multiplying the density times what? Times the volume. It doesn't have to be in liters. It doesn't have to be in liters. Let me just put this as 4. We have 5 here. These are 5 equations. These are 5 equations. I can even add the sixth one here, which we just used it last week. M1 equals to M2 V2. This is dilution what? This is dilution equation. Dilution equation. We should be able to use those equations we will use in today's lab. I will kind of like overview the concept of titration, because when you move on to Chem 2, all right, you'll be expected to know some of the terminologies associated with acid, base, neutralization, or what is basically neutralization, right? Neutralization is a type of reaction where, all right, hydroxide react with hydrogen ion to produce H2O. This is from the base, and this is from the acid. We call this acid-base neutralization. Stoichiometry comes in here, that mole ratio for this is 1 to 1. You know, the mole ratio, the coefficient in the balanced equation. So a type of double replacement reaction where hydroxide combined with hydrogen ion is categorically called, or specifically called, or classified as acid-base neutralization. So any compound that produces OH is a base, and anything that produces hydrogen is an acid. Let's a real quick look at the background information on acid-base, all right, acid-base titration, or titration of neutralization reaction. Basically, the compound or the solution which goes in the puree, we call this the puree. This is the stopcock. You turn it on. Perhaps some of you have used. We call the titran. What goes in the puree is the titran, and what goes in the flask here is called the analyte. You may see this down the line. We call this analyte, what you are analyzing. And quite often, the titration technique is used to determine the concentration of a known solution and analyze. So if we know the stoichiometry, the reaction between the mole ratio between the titran and the analyte, we use the titration technique whereby an organic compound called the analyte, in this case, is an organic compound called the indicator, is added onto the analyte solution. When you continue adding the titran into your solution, into your analyte, at the end point, the solution will change color from my left uh, flask. There is, all right, there is the pink container, which indicates that the titration is complete. So with that, we will have to, all right, we'll have to stop the titration. And if we know the volume, all right, if we know the volume used to titrate the analyte, we can use the stoichiometry to find the mole ratio and know the number of moles in the analyte, and the we find the concentration. We'll find the concentration based on that. I can see my cursor key. Let me see if I can. I guess it's just disappeared. Hold on. I'm just going to see. If I can take back to where we are, the analyte. Yeah, so this is the final solution. Once the titran neutralize or consume the number of moles in the analyte, we stop the titration and calculate how many ml of the titran from the puree have been used to consume the number of moles in the analyte. If we know the number of moles, if the mole ratio is 1 to 1, we use either the dilution law M1, M2 to find the number of moles, So here is our analyte, and the Titan goes in the purette. You need to know the class we use in this titration technique. So the setup look like this. We call this purette stand. All right. LMR flask, and there is the purette clamp here. And by the end of this, there's some terms you need to know. The process by which you add small amount of titration into your analyte is called titration. Perhaps you have done this experiment or performed this experiment before. We call this titration. Or there are some points along the titration curve we call either the endpoint or equivalent point. All right. Before we get to this, standardization is making sure that we know the exact molarity of the titan which goes in the puree. Quite often, for example, sodium hydroxide, when you prepare a certain concentration of sodium hydroxide, NaOH, used in titration, the concentration keeps on changing over time. Let's say we make a solution of sodium hydroxide today, and we store it until tomorrow or next week. Over time, the concentration keeps on changing. So chemists do what we call standardization. That is a process by which exact concentration, exact molarity, concentration and molarity are often interchanged, typically used to make sure that we know before we use that as our titrant. So before we fill in the period here with our NaOH, we need to standardize by using what we call the a primary standard. In this case, KHP, uh, potassium hydrogen thalate, which in part A of today's experiment, we will standardize the titrant, which goes in where? In the puree. And at the end of the titration, once the standard solution which goes in the puree have been determined, exact concentration is used in titration. The titrant is what goes in the puree, and the analyte is what you are analyzing. From the word analyze, what you are analyzing. What goes in the flask is the what goes in the flask is our analyte. We call it analyte, and the data analyte will be a solution of vinegar. I'll get to that. How will you know that it's time to stop addition of the standard solution? Is by paying attention to the endpoint. Endpoint is an estimate of equivalent point. Endpoint is a point in titration whereby you need to stop addition of the titrant into your analyte, and it is signified by change in color. You see this endpoint? We know that it is time to stop. If using phenolphthalein, in this case, this is the indicator, we are looking for a faint pink color which lasts for about 30 seconds. You don't want to have like intense pink. This is over titration, over titration. So just look at that. And this endpoint indicates that it is time to stop the titration, which in essence, this is what you're looking for, equivalent point, which means you have equal number of moles of the acid, equal number of moles of the base. At the equivalent point, we have a stoichiometric amount. When we say amount here, we are talking about what? About the number of moles of the acid and the number of moles of the base, number of moles of the base. So our indicator today is phenolphthalein, which is colorless in acidic solution, and in basic solution, it's pink. It's pink, all right? There are two separate acids will look or will be used or which were used in this experiment, and these are the KHP. This is the chemical formula, all right, and this is the we call this potassium hydrogen thalate. In the pre-lab assignment, wherever you are asked to find the molar mass, I see students taking the atomic mass of potassium, adding atomic mass of hydrogen and atomic mass of phosphorus and assume that, oh, this is the molar mass of KHP. No, this is the abbreviation, but the actual chemical formula is given right here. So you need to account for four oxygens, four hydrogens, eight carbons, one potassium, and one hydrogen when you are calculating the molar mass. We need to know the molar mass of that. And of course, the other acid is the vinegar. So this is an acid, this is an acid, and this is the titan which goes in the puree, in the puree. You know the puree? It's the long class, all right? The long class apparatus used in titration, I don't want to go through the titration curves. You will cover this in Chem 2, Any question before we dive into the data sheet? I'll get into the data sheet in a minute, but what you see on the screen are the apparatus you are to use in this lab. Analytical plans for weighing out the solid reagent, all right? This is for weighing out the mass of KHP, potassium hydrogen thalate, so that you find the molarity. This is the purette stand, purette clamp for holding the purette. This is the purette LMR flask. And this is the pipette, all right, with the calibration mark here. The edge mark here means, or it indicates that if you pipette your reagent up to this, when you have the meniscus, that is the exact volume of your solution. It comes in different capacities. There is 25 ml volumetric pipette, there is 20, there is 15, there is 5, they're even smaller than that. So if you need 10 ml exactly, you're gonna look for that one with 10. I think this is 25. And you always have to use the pipette bulb or filler to pipette the solution, then you transfer, and then you perform the titration. So look at the reagents. This is potassium hydrogen thalate, the chemical formula I showed you in the previous slide. Please do not use this to find the molar mass of KHP and say, all right, the instructor gave me the chemical formula for potassium hydrogen thalate, and it's very easy to find the molar mass. Look at the chemical formula. Sodium hydroxide is dissolved, is what goes in the puree, and phenolphthalein is used to indicate 2 to 3 drops to indicate the endpoint. In part P or part 2 of this simulation, this experiment is we will find the mass percent of vinegar. I mean, mass percent of acetic acid in vinegar. You know how, you know the taste of vinegar, right? Okay, let me just stop and see if some people have tasted vinegar. What is the taste of vinegar? Let's see. Can somebody just use the chat room and, have you tasted vinegar? Not in the lab, but at home somewhere. You know vinegar. Yeah, it's acidic. Yes, thank you. Thank you, Margaret. Let me just go back to my screen here and right here. This is what is present in vinegar. So when you are in Olive Garden or, Subway and say oil and vinegar, that tincture test, that bitterness in vinegar is the acetic acid. So we will analyze a solution of vinegar which has acetic acid at the end, In the data sheet, there's somewhere which will call for balancing the equation, all right? We'll come back to that. This is just, safety precaution. If we were to come in the lab, we always pay attention to the safety. Here is now information you need along with the information on the top hat, what you see on the screen, and this is a PowerPoint slide available on modules. For this experiment, you need to go to this slide, all right? You need to come to this slide in order to, all right, in order to complete the data sheet. Let me minimize this and I will reconcile this with the data sheet. I'll reconcile with the data sheet. This is the data sheet, all right? And if you look at this part right here on the data sheet, and please read the what? Read the information from top hat. I'm just showing you how to fill. You will have to write the every information. For example, here, fill in your name, section, and the date. Of course, you're just working by yourself. All right. In part A, write the balanced equation between, all right, between KHP. This is standardization of sodium hydroxide. When it says standardization of solution, this is solution here, solution of NaOH. Look at my PowerPoint slide here. This is NaOH being standardized. So this solution being referred here is NaOH. From the PowerPoint slide, you see the balanced equation here. This is what I need to be on the data sheet at the top right here. Balanced equation, this is the balanced equation. And if you look at the mole ratio, it is what? It is 1 to 1 to 1. It is 1 to 1 to 1. If I look at the mole ratio, please pay attention. There is one there, there is one there, and there is one there, there is one there. We need the mole ratio. Mole ratio is 1 to 1. For every 1 mole of KHP that is consumed, 1 mole of NaOH is dropped into the reaction flask. Balanced equations convey the message of molecular stoichiometry. All right, molecular stoichiometry. Let me clear the screen a little bit. All right. So that is what I will be looking for balanced equation. You need to read the background. It's in top part. You're given here. Now, the mass of the flask, there is trial 1, trial 2. You don't need trial 3. Just cross out this. It is not necessary based. Oh, we have it here. So it was necessary for him to do that. For trial 1, trial 2, trial 3. So it was necessary mass of the flask and KHP mass of LML flask by itself. The purpose of this is to know the mass of what? To know the mass of the KHP. I was just scrapping something in my office. This is the flask. You can see that. So you just have to weigh, or it was weighed by itself. And the mass of the flask here, you get from the PowerPoint slide. Mass of the flask. This is just mass of the empty flask goes at the top. Mass of the LML flask with KHP. So line 2 here minus row 1. Let's call this row 1. Row 2 minus row 1 give you the mass of the KHP in the flask. You have to find the difference. We are looking for the mass of the KHP. How will we get that? Line 2 or row 2 minus row 1 give you what? The mass of KHP. This is what I was talking about, that you will need this information which we learned earlier on. We are looking for what? We are looking for number of moles of KHP. If I know the mass, somebody has a question? Are we going to, yes, trial 3, you'll do trial 3 because we have trial 3 here too. Yes, there is trial 3 here. You see this is trial 2, trial 3. So this minus that, this minus that, this minus that, give you the mass of what? Mass of the KHP, mass of the KHP. I know in the pre-lab you are asked to find the molar mass of what? molar mass of KHP. Please don't make a mistake of just using potassium, hydrogen, and phosphorus. So that to get the number of moles, look here, number of moles of KHP is obtained using equation 2 here. Equation 2, I know the mass from here, and the molar mass you can find from, using the periodic table, to get the molar mass of this fast reagent. So I guess if I can put side to side and just try to load this a little bit, we may have enough room to see what's going on. So calculate the number of moles. This is given by what? Mass over molar mass, mass over molar mass. And then titration, filling the what? Filling the puree with the with the NaOH solution, making sure that there is no air trapped in there. All right. You read the initial volume. So it was at 0, 0. All right. It was T0, 0. You know how this works? I see student making mistake. This pipette, or I mean puree, the 50 ml mark is somewhere here. And then the 0 ml mark is at the top right here. So always you read it is upside down. It is not like the graduated cylinder. You know, the graduated cylinder gets filled up like from 0, 1, 2, 3 to 10. But this one, you are coming from 0, 1, 2, and then whatever it will stop, we call it the final. Where it was starting, where the meniscus was starting at the top, we call that initial volume. So initial volume in trial 1 started from 1, and it ended at 18.30 ml. And please use 2 places of decimal. The volume of NaOH used, all right, the volume of NaOH used to titrate fast trial is the difference. Final minus initial is the volume of NaOH. Final minus initial give you volume of NaOH. And remember, this is what? This is volume in ml, not liters. Volume in what? Volume in ml. You knew the number of moles of KHP, from here, all right? Number of moles of KHP calculated. Critical thinking here, if I know the number of moles from the balanced equation, and that is why you are asked the balanced equation, if you know the number of moles of moles of KHP from the mass of KHP and the molar mass of KHP, the balanced equation tells you mole ratio. If I have 2 moles here, then I should get 2 moles here. If I have 3 moles here, I should have 3 moles. If I have 4 moles, I should have 4 moles of that. So there is no calculation in this case. It's just like the numerical value for the number of moles of KHP is the same as the numerical value for the number of moles of NaOH in each trial, because the stoichiometry is mole to mole. In case you want to write the in calculation, show me how you arrive at that. I'll say maybe this was the number of moles in number of moles of KHP. All right. If this is the number of moles of KHP here, so I can write so fast using my mouse. KHP here. All right. XX is the number of moles of KHP, like that. And then I'll use now the mole ratio. For every 1 mole of what? For every 1 mole of all right, OH, like that, that is consumed, 1 mole of what? 1 mole of KHP consumed. This is from the balanced equation. I'm just showing up the setup calculation for the number of moles here, the number of moles of NaOH, line 4 here. You see line 4? This is how you set up the equation to get the KHP, number of moles of KHP. If I cancel that, that will cancel, and that will cancel. That will cancel, that will cancel. All right. And you have the number of moles of NaOH. And of course, the equation here is just used to find the number of moles of KHP. You see this equation? It is from here. That is what we are looking for. Any question on part A? All right, what I'll do is I'm just going to clear everything here, and I'll move on to the second part, all right, which is once we know for each trial, all right, for each trial, number of moles of NaOH, all right, number of moles of NaOH. Now, molarity of NaOH, all right, molarity of NaOH, you have to use the equation we looked at from here. This right here, line 5, molarity is given by number of what? Number of moles of NaOH over what? You have to change the volume to liters. You know the volume of NaOH used in each trial. This is volume in what? Volume in liters of it. You have to show me the calculation that this is number 5. All right, trial 1, trial 2, trial 3, and then you show the calculation. From the number of moles and the volume, please change this to liters divided by, number of moles for trial 1 over volume in liters for trial 1. Number of moles over volume in liters. Number of moles over volume in liters to get the molarity for what? Get the molarity of NaOH solution. And of course, you know how to find the average. 1, trial 2, trial 3, and then you divide by 3 to get the molarity. So we have standardized the what? The NaOH at this point, which we need to use now the standardized solution. We know the exact concentration of NaOH at this point. Once you determine the concentration of NaOH, we will use in part P. In part P, let me just save this and I will clear before I move on to part P. Any question? Any question before I move on to part P? All right, if there is no question, part P or section 4.4 is determination of mass percent of vinegar, mass percent of acetic acid in mass percent of acetic acid in vinegar. So there is the vinegar solution, and then there is the acetic acid. Acetic acid is in vinegar. Let's understand that so that when we crunch the numbers, when we do the calculation in part 2 of this experiment or section 4.4, we keep track, we keep an eye on what is what. There is acetic acid in vinegar solution. There is vinegar solution which has acetic acid in it. NaOH will react with acetic acid in vinegar, but it is not the other way around that NaOH will react with vinegar solution. No, essentially, what is reacting in vinegar solution is the acetic acid, which we are now going to use our standardized solution from part what? From part A to determine the mass percent of acetic acid. So vinegar solution has the acetic acid. And this equation, look at my cursor key. This equation, acetic acid reacting with NaOH to produce sodium acetate and H2O, don't ignore the fact that mole ratio, let me just even use a different color here, mole ratio is 1 to 1 to 1. We care less about the product side. Mole ratio is 1 to 1 to 1. So this is the equation you need to write at the top of what? At the top of the table on the data sheet. You need to fill in that. This is the equation and it's available in the background procedure in Topaz as well as the PowerPoint slide. So let's see in part 2 or section 4.4, there are two trials, trial 1, trial 2. And since we had only one solution at this point, you will write down the concentration of NaOH from table 4.3, the average. Remember, you had three trials, trial 1, 2, and 3, and then you had to find the average. You'll end up with one value, which you will bring it down here. All right. So if you look at here, unless you read the background procedure in Topaz, you will not know what was the volume of vinegar. The direction called for using the pipette to pipette 10 ml. All right. So at this point, this is what they used. The instructor, whoever used this piece of glassware with a capacity of 10 ml with a calibration mark using the bulb, all right, and 10 ml were transferred into LMR flask, and the titration went this way. 10 ml of vinegar, 10 ml of vinegar. So you know the volume of vinegar used, not acetic acid. Don't think that we are pipetting acetic acid. We are pipetting vinegar solution with vinegar in it. And what will react in vinegar is NaOH, is the acetic acid. Acetic acid in vinegar will react with NaOH from 4.3. Well, titration, just like in part A, initial volume, the meniscus was at 0, and then it dropped down to 20 ml, and boom, the color changed from colorless to pink or faint pink. And the instructor had to stop the titration. Final minus initial will give you volume of NaOH used to titrate the vinegar solution to endpoint. You'll do the same thing for part or trial 2, starting from 20.10. They didn't refill to the pipette, they just continue from what there as our initial, and the final is 39.60. So 39.60 minus 20.10 ml gives you the volume of vinegar for trial 2. If you look at the data sheet here, final minus initial gives you what? Gives you the volume of vinegar. Now, not volume of vinegar, volume of NaOH. Let me pack up to first line 8. You see line 8? Mass of vinegar. This is what I was talking earlier on about, you know, there are some prerequisite there was some prerequisite equation. I'd say that you need to know. If we know the volume of vinegar here, you see this volume of vinegar used, this is the volume right here, this is the volume right here. We use the density equation to find that. This is how you will arrive at line 8. This line 8 here, maybe red will work. Line 8 here, this is what we will do. Mass from the density is given by density times volume of vinegar, which you know. You don't have to have it in liters. This is the density Y you are given. This is the density, which is this value here. And the volume is given, or it was stated here for trial 1 and trial 2. To get line 8, mass of vinegar solution is given or determined by multiplying the volume with the density. I know the what? The density is given here, and I'm given the volume for each trial. And of course, you find the difference. Now, coming down here, number of moles of NaOH, number of moles of NaOH used, all right, to reach the equivalent number of moles. Remember, here we know molarity. You know the molarity from part. This is the average. You see this molarity here. This is what you will use. Molarity of NaOH is given by number of moles. Here, number of moles over what? Number of moles over volume in liters. Volume in liters. Which volume in liters are we talking about? If I know the volume of NaOH here from line 9 here, change to liters, because that's the volume used to titrate the vinegar solution. What was the input? What was the volume of NaOH used? Number of moles, you know what? You know this from line 7. You see line 7 here? This will be your here. And then from line 9, you have to change that to liters, which means number of moles is given by molarity times what? Volume in liters, volume in liters. That's what I'll do for line 10. For line 10. Molarity, this is the average. Volume is the volume to reach the end point. And you remember to change to liters. You know how to change to liters. You divide by what? You divide by 1,000. You divide by 1,000. Line 11 here, let me just save this and I will clear. To get line 11 here, the mole ratio from here, look, mole ratio is 1 to 1. So if I know the number of moles of, all right, this is what I'll do, XX moles of what? Moles of Na, all right, NaOH, this is the setup, times now the stoichiometry in the balanced equation here. This will be moles of what? Moles of NaOH, all right, this is NaOH like that. Number of moles of NaOH, this is 1, all right, and then for every 1 mole of acetic acid, acetic acid, you've got to write the chemical formula for that. Acetic acid, I'll cancel that and I'll cancel that. It will just be the same because it is 1 to 1. This is just a setup for finding the number of moles of acetic acid. It is based on the stoichiometry in the balanced equation. Stoichiometry in the balanced equation. And that will give you number of moles of acetic acid for trial 1 and trial 1. Trial 2, trial 2. Now, to get the mass of line 12 here, line 12 here refers to mass of acetic acid, which is this now? Not vinegar. We have changed the terminology from vinegar to what? To acetic acid. It is given by, all right, this is given by the number of moles, all right. You know the number of moles now from line 11, number of moles of acetic acid, all right. times what? Number of moles times the molar, let me abbreviate that, not molarity, but mm, uppercase M for molar mass. This is from the what? This is from the periodic table. This is from the PT. PT stands from the periodic table. How? If you look at this is the chemical formula, and you should be able to find the molar mass of acetic acid. You know the chemical formula. One hydrogen, four hydrogens, two carbons, and two oxygen. Find the molar mass. That will be your molar mass times the number of moles from line 11. That will give you the mass of acetic acid. Mass of acetic acid. We are rearranging that equation I showed you earlier on. That number of moles is given by mass over molar mass. So if we multiply the number of moles times the molar mass of acetic acid, we will get the mass in grams. And by the way, this will be in grams. Please, the units, all right, the units. Include the unit reconciliation so that you have the units for molar mass. So line 13, all right, line 13 here is the mass percent of acetic acid in vinegar solution, which will be line what? We know this is line. We know line 12 over line what? Line 8 times 100 what? 100%. This is how to get the mass percent of vinegar. Mass percent of acetic acid in vinegar. Line 12, which is the mass of acetic acid, over line 8, which is the mass of vinegar. Mass of acetic acid over mass of vinegar times 100 will give us the mass percent of acetic acid in vinegar solution. All right. Now, line 15, there's no question. Line 14, sorry, molarity of acetic acid in vinegar. We know molarity is number of moles over volume in liters. You can use the moles of acetic acid. Do we know the number of moles of acetic acid? Yes, we know the number of moles of acetic acid. So this will be line what? This will be line 11 of volume in liters. This is volume in liters of the vinegar. Remember, here was the volume. Look at the volume. This is the volume of the vinegar solution. This is the volume of vinegar solution in trial 2. So you can change this volume to liters. Molarity of acetic acid in vinegar sample. This was the volume of the vinegar. You know, moles over volume in liters gives us the molarity or concentration. We know the number of moles of acetic acid from line 11. That's why I have here line 11 over volume in liters, which is here of the vinegar solution, gives you the molarity of what? Molarity of vinegar, molarity of acetic acid in vinegar solution. That's what we need to remember. Change the volume to liters. This is the liters. This is volume in ml. And you have to do for trial 1 and trial 2. And then average mass percent, all right, I know the mass percent here. This is trial one, this is trial two. What is the average mass percent? Average mass percent is the sum of the two here. All right. Sum of the mass percent of trial one, trial two, you find the average. Please show the work. Don't just write one value and say the instructor will figure it out that I had to add the two and divide by two. Previously, I saw a student saying that it is in my calculator. I don't have your calculator. Yes, I saw somebody saying that it is in my calculator. They just wrote one value and say it is in my calculator. Okay, bring your calculator and then I see. And then lastly here, average molarity. Of course, if you know the molarity from line 14 for trial 1, for trial 2, you'll have to find the average to get the average molarity. That is what I want you to do, show the calculation. I wanted to walk you through on uh, completing the data sheet and pointing out some of the prerequisite concept you need to bring over to this lab so that you move ahead with the calculation. With that, let me just pause for a minute and take any question you may have before I make the quiz available for you. Is there any question, everybody? Is there any question, everybody? I should have saved this. Let me just save this, and then I'll share that. Any question? I'm gonna clear that. Any question? If there is no question, thank you for joining Zoom this afternoon. If you are in the session, can I get a thumbs up on the thumb room? I want to see people who are just logging in and leave. I'm gonna take a roll call and see real quick random check. Can you press? Yeah, I see. Uh, Ania, I see. Evan, all right. Okay, Alexandra, Marshall, I see. All right. Robbie, yes. Everybody be yeah, yeah. I see some people if you don't and then they look. I see hope. All right. Thank you, thank you, thank you. Sarah, I see you. All right. If you are in the chat room, please press thumbs high, high five. I see a thumbs up. Some people they look, but nevertheless, I'm gonna stop here. I'll be in this Zoom conference. You don't have to be in the Zoom while taking the quiz. Right now, it is 1:55, so around 2:30, you should be done. I'm just gonna stop sharing my screen now, and I'll make the quiz available. Thank you.